Swayam Prabha. Digital India. Educated India.
So far we have seen the paradigms of protection, overcurrent protection, distance protection, issues affecting distance protection. Today we will go on to what is virtually part 2 of this course, which is numerical relaying, fundamentals and realizations. Now, the principles that of protection that we discussed so far, overcurrent, directional, overcurrent, distance, can be realized using electromechanical methods or static circuits, or even with the use of computers. I use the word computers a little loosely here. We will refine it as we go along today's class and maybe the next lecture. The electromechanical relays were have served predominantly from the beginning of networks and transmission and distribution networks till about the 80s or mid 80s or 90s. Then static relays slowly took over, and now is the era of numerical relays. In fact, the next era of VAMs devices and PMUs and relays functioning as phasor measurement units is already upon us. We will see some of that in part 3 of this course towards the end of when we are just finishing this series of lectures. One straightforward method is whatever was the electromechanical relay, we just go over to the or just transform into the computer version of it. Even that is possible, and that will also give certain advantages like reduced cabling, reduced burden, because the electronic circuits don't actually require power to turn a disk or generate any torque. So the VA burden is very less, and we have seen what happens when if the VA burden is high and how CT saturate and all that. So that in itself, if you just make a realization of the electromechanical circuit into a computer relay, even that will have enough advantages. But that is actually not exploiting the full potential of numerical relays. So the actual exploitation will come, or the actual benefits rather will accrue when you actually use innovation, use your ideas to implement whatever is the full potential of the computer, not just the relay. The relay you can realize using the same principles, okay, and then multiply the benefits that you can get from the application of numerical relays. So basically numerical relaying, as the name suggests, is nothing but realization of a relay on a logical element, that is the computer. Okay. So in numerical relaying, this as you would have guessed, because our signals are all analog, so it will involve some kind of signal processing where you have to filter the analog signals. Then there will be some digital filtering, like say discrete Fourier transforms. We will look at all this in detail a little later, maybe 2-3 lectures after this. Then after that, after this is done, after the filtering, after the analog filtering, the digital filtering, then you extract the phasor. Once the phasor is extracted, you can apply the same relaying principles like overcurrent, distance, etc. The only caveat here is that all the processing has to be done between to sample. So, if you have a high sampling rate, your processing time will also reduce. Now, that in itself is not a big challenge, because nowadays the processors are as powerful as you want them. In earlier days, this was a challenge because the processors, the computers were slow, and if you went beyond a certain number of samples, then your processing time reduced, and the processors would get overloaded and would not function optimally. Of course, one reason for that is because if the even though the newer versions keep coming out and faster processors are available, you simply cannot use the next available fastest processor, because here it is a tried and tested hardware. It has been tested for EMI, EMC, that kind of compatibility, and so you tend to be a little a step or two behind the fastest available kind of processor. Okay, so coming back to numerical relaying and its advantages, one is, of course, even if you simply replicate the application, you will get benefits in terms of the reduced cabling, the reduced VA burden, etc. Now, but you could use so many other maybe features available with numerical relays to fully exploit that. I'll just give you an example. You could, because this is numerical relay, and you just imagine it as a sort of a computer. Then you can have all those various communication ports. It can communicate with the substation host computer, and you can have a substation LAN where all the relays can put the information that is available to them, and you can utilize that. The relay can utilize that information also. So, if, for example, if in a traditional current differential scheme, you did not have the information of the voltage, and say if you are doing a current differential protection of a transformer, then if there is an inrush current, then you will have to have some ways of restraining for that, second harmonic restraint or something like that. But now, if you know the flux present in the transformer, if you could somehow measure it using a PT, and that information can be made available to this numerical relay, then you can design a better scheme for inhibiting the relay tripping on inrush currents. So, there are advantages like this. Plus, in earlier days, you did not have, the relay could not store any data. Now, one of the major advantages of numerical relays is it can store data. Whenever there is an event or a tripping or some transient event, you can get the relay's data storage is triggered, and you get up to about 5 cycles before the event and some after the event. These are available in different formats. The most commonly used is the COMTRADE format. Then you can download it from the relay and do your own analysis. You can download such files from multiple relays and then build a picture, sort of a post-mortem of what actually happened, which relay tripped first. Of course, for that you need accurate time stamping also, which can be done with GPS. But even if that is not done and not available, there are some signatures which are available in the network, like line trippings, etc., where you can use data from various relays. You just have to align it. Of course, just have to align it is not as simple as it sounds. It would take some time, but it can be done. With electromechanical relays, there was no way, or even static relays, there was no way to just download the data from the relay and sort of replay or use it for post-mortem analysis. You needed something. There were other devices known as fault disturbance recorders, which actually worked only to record the data. They were not relays. So, you needed a FDR with a high, FDR means fault disturbance recorder with a very high sampling rate, so that it could track transients, etc. And then you could download some data from that. Now, with the numerical relay, you can still have FDRs, but you can directly download data from the relay and do your post-mortem analysis. So, Here we will have a look at a few slides on numerical relaying. This is just sort of today's lecture is a sort of an introduction to numerical relays. We will look at some aspects like the sampling theorem, the estimation of phasors, and then go on to estimation of frequency, etc., in great detail, so that you know how a numerical relay actually computes things. Okay, so we will have a quick look at a few slides on numerical relaying, and then go on in subsequent lectures to discussing each of this in some more detail. So, why numerical relaying? We have already discussed some of the aspects of numerical relaying. We will quickly go through them in any case. So, yeah. So, these some of these we have already discussed, but we will discuss very quickly, so that since we are on the topic, we will discuss them quickly once again. We discussed that they are very load burden because they are just sort of chips which where the power consumption is very low, so they do not require any power to drive electromagnets or even op amps in the case of static relays. So, now this last point I will come to in a bit. We will first discuss the 2-3 points that are above. The first one is to improve dependability as well as security. We have seen these in detail. This two parameters define the overall reliability of the relay. Dependability is tripping when required to trip. Security is the sort of the complement where it should not trip when not required to trip. So, with numerical relaying and better processing and more awareness of non-local data, that is global data. You could have data from the other substation because communication is now available with the relays. Earlier also it was not that with electromechanical relays there was no communication. There was communication, but you required things like couplers, etc., to be able to communicate data from one relay to another or one substation to another. With numerical relays, it is like a computer, so you can hook it up to a network and you can communicate, or the relays can communicate. One facility which was not there with electromechanical relays, but was there with static relays and is similarly present with numerical relays, is self-checking facility. So, you can have a continuous check of whether all the parameters are okay, whether all the boards are working okay, whether the power supply is okay, etc., and give an alarm or a flag if it is not okay. As we have discussed earlier, relays are devices which sometimes may not be called to operate for months together, and it is not like you operate a relay every day or every other day. It can just sits there in the network waiting for a fault, and if that particular part of a network is not particularly prone to faults, then maybe the relays may not operate for months or even years together, and when called to operate, it may fail. So, because something has gone wrong. With electromechanical relays there was no way to know, but with static and with numerical relays, more so with numerical relays because there are more functions available, you can have a proper self-checking facility. Now, if immune to variation in parameters of individual components. Now, things like op amps or capacitors, the values can drift. Okay, there are parameter drifts that are present. So, maybe the settings could change, or the relay could maloperate, but with numerical relays that is less likely, because you have say a 0 to 10 volts, anything below 5 volts is 0, and anything above in between 5 to 10 volts is 1. So, it is a binary kind of logic. So, if there is some variation, as long as it is within that range, it will still be 0 or 1. In fact, that is one of the reasons why why the binary kind of logic is used. Otherwise, you could have had 10 levels of 1 volt each, or if it was 0 to 5 volts of 0.5 volts each, and then you could have implemented a decimal logic directly, but that does not happen. So, that would make it more vulnerable to drift, etc. So, we stick to that binary kind of logic. So, the parameter drift does not affect the performance of the relay. Now the low burden we have discussed, of course. Now the flexibility because of programmable capability is something that you have to think for yourself, feel for yourself. Otherwise, it's just an implementation of the electromechanical relay. So whatever you use, whatever your innovative thinking is, you could use. For example, I'll just give an example. Is earlier if you needed say a 3V0 kind of voltage or a V0 that is the zero sequence voltage to implement in some maybe some unbalanced voltage scheme or something. What you would have to do is you would have to say connect 3 PTs in an open delta formation and VA get VA plus VB plus VC there which is nothing but 3V0 and then implement the scheme. Or if you needed the zero sequence current to implement some ground fault kind of scheme, then you actually have to put a CT in the neutral and then calculate the neutral the zero sequence current which was 3I0. But now with numerical relays you already have IA, IB, IC or VA, VB, VC available to you. You can just program it and get an average IA plus IB plus IC or VA plus VB plus VC by 3 as the case may be and get IA or I0 or V0 respectively. So there is a lot of flexibility, lot of reduction in wiring, devices, all this, these kind of advantages. But you have once the parameters or the quantities that you want are there in the computer, you have to think of how to optimize and utilize these quantities. Okay. One thing is, now almost all new relay installations are numerical relays. So you actually need not justify why numerical relaying, but we are just listing out the advantages of numerical relaying. So with a computer kind of, when I say computer, I'm meaning at a conceptual level. You just cannot take a laptop that is available to you and then put it and expect it that it will perform as a relay. There are other issues. Substation is a noisy environment, noisy from the point of view of electromagnetic noise. There are switching going on, there are cables, there are interference voltages, etc. So in that sense it is a noisy environment, so it requires some EMI or EMC kind of hardening before it can be used in that. But at a concept level it is still a logical unit or a computer. So once you have a computer, then you can have communication ports, you can have you can network them, form a substation LAN, you can have fiber optic communication ports, you can have Ethernet ports, whatever is your requirement or your design requirement, you could specify the relays accordingly. One more advantage is adaptive relaying, either through some external input or through external data available from other relays. You could do adaptive relaying. Adaptive relaying is say in an electromechanical relay, once you set the parameters, unless you went and changed it manually, there was no way to make it adapt to any kind of network situation or load situation or things like that. Because say for example in the night your load is very low, so your generation is low, your settings may need to have to change. But with numerical relays that is possible. There are things known as group settings. So where you have one group of settings for one particular condition, another group for another condition, and with an external trigger like a digital input, some breaker status has changed or some, usually a breaker status, you can wire it and change the settings according to the change in the network settings. So that is adaptive. So it adapts to change in the settings. This we discussed that data can be stored, since it's it's a computer like device. You can have storage and you can have memory and you can have data to be stored in these things, and of course the memory is limited. So if you want if you want some kind of data, then you'll have to download that data and use it, otherwise it will be overwritten. It is not that data is forever available to you. That will require a lot of storage and it may not be necessary also. One advantage in recent times is you can the clock that is used for sampling can be the GPS timestamp, GPS time, so that you can do simultaneous sampling all over the network. And this came mainly with phasor measurements unit, which we will discuss a little later. But now for relays also this is available, and you can use the timestamps as you can either have a direct GPS receiver, or the relay has a port known as the timing port, the IRIG-B port, where you can give a signal which is available at your substation from a GPS, and you can have a proper timestamp so that you can compare data across locations also. If you in case you are wondering, the GPS is not only used for geolocation, where you find the location of a particular point, or when you are traveling you need a GPS device. GPS also, the GPS satellites also provide timing pulses, which is 1 pulse per second. We will look at it a little later, so that that can be used as, because we don't need the geolocation facility of the GPS, because our substations, our relay locations, etc. are fixed, so we don't need that, but we utilize only the timing pulse from the GPS. So moving ahead, let's look at some traditional architectures, and then we will look at how this changes in a numerical relay. So first we look at the substation architecture. Here you can see that this is a more traditional architecture. It doesn't really matter whether the relays are electromechanical or static or numerical. The relays here on the you can see the box, the green and red. You will have to use all a lot of wiring and cabling, etc. to get the relay data to a common place, relay data, the control data, and then you have to, if you want to communicate with other units, you will need something known as, you can't there is no the device which is capable of directly communicating. So you will have to go through what is known as a remote terminal unit, which is used for communication with other. This is the basic unit of SCADA, RTUs as they are called, and then there is a communication interface, and you can communicate to other substations or other elements in the network. Now, one thing to remember here is that since there is no common time reference available, you cannot really use phasor data. So what you do is you use generally you in SCADA the real power, reactive power, which are not phasor quantities, they are scalars. So there is no angle information is masked because you use VI star. So angle information there is masked. So you use quantities like voltage magnitude, real power, reactive power, etc. For your other computations. With numerical relays on the other hand, you can use phasors directly if of course the common time reference is available. But even without that, the architecture, as you can see, is quite simplified. Everything can be put on the on a LAN. So this kind of architecture is already is with us. It is not futuristic. It is already there, and is what are known as digital or automated substations. You can have a substation LAN and all the devices putting all their data on substation LANs, and then that can be used for communication. You can have a substation host computer also to monitor and look at data, and use it for protection actions, control actions, etc. You can see that the layout is much simplified. In a small substation, the wiring, etc. Even though substantial doesn't matter much, but in a large, very large 400 kV substation, which handles say 1000 megawatts of power, the cabling itself there are kilometers and kilometers of cabling. So even that can be avoided, and simplified. It is a big plus for the operations engineers, for the maintenance engineers, for the protection engineers, for control engineers. So, this is one of the ways we can leverage the power of numerical relays. Okay. So, yeah. So, this we discussed. This is the open delta configuration of PTs or potential transformers or voltage transformers. Here the delta is kept open, and since it measures VA plus VB plus VC, you get 3 V0 at the output. Then you can use that V0 for sensitive voltage scheme or whatever scheme that you design. This whole thing could have been avoided. You can just do a VA plus VB plus VC which is available in the numerical relay itself. So, you can do that and avoid all this complexity. Sorry. Okay. So, just to conclude about numerical relaying, they are the best compromise between economy and performance. Now, silicon devices are very cheap nowadays. Okay. Of course, there is a cost of the proprietary algorithms, etc. that goes into the relay, but as such, if you were to manufacture a fresh numerical relay versus an electromechanical relay, the electromechanical relay would turn out to be costlier than the numerical relay. Okay, you can improve dependability without compromising on security and vice versa with numerical relays, of course with information from other locations. So, that kind of you do not have to really compromise between dependability and security. Complexity and simplicity. The complexity can be there in the algorithms and the implementation, but the utilization or the use or the for everyday engineers who are there in the substation, it is simple to use. So, in case you are wondering with so much hardware and software and all that, is it not complicated? Yeah, that side is complicated, but for the user side, it is simple to use. Speed and accuracy. So, you can have the relays can be fast as well as, because you have multiple checks, etc. They can be accurate also without, you can speed up the decision making without compromising on the accuracy. One word of caution here is, just because they are numerical and we would assume that any computer is faster, in all applications numerical relays may not be faster than electromechanical relays. One application is a distance relay, where in a numerical relay you have to compute the phasors and then take the ratio and all that. So, that whereas in an analog kind of relay, electromechanical relay, you can just do directly, it can do a V by I kind of calculation. Okay. So, just because it is numerical does not automatically imply that it is a faster relay. So, that is one word of caution. You have to, because there is time, we will see when we do phasor estimation why it requires time, and you require at least half a cycle, usually one cycle, because you will use a full cycle DFT kind of algorithm to estimate your phasors. So, the point is that though we say that it is the best compromise between speed and accuracy, being numerical does not automatically imply that it is faster. Okay. So, credible and conceivable, I mean, if you can design the algorithm, it can be easily conceived. Okay. So, we will just quickly look at the blocks just for today's class, and then we will move on to discussing some of those blocks. So, you will of course require an analog subsystem, because you have to interface with your voltages and currents, which are analog quantities. Then you have to you will require conversion to the digital form, since your heart is a computer. So, you require to get the analog values into digital. So, you will have an ADC, then you will have some filters, digital filters, and then you go on to for processing into your hardware. Then after that you will require some output, because that output, once the computation is done, the decision to whether to trip or not trip has to be outputted. So, we will require some digital output system, and some processing, for running your algorithm, for taking the relaying decisions. You will require some processing unit with memory, some ROM, some RAM, where in the ROM you can store the algorithm. The RAM can contain data which you get from sampled values, etc. And to power all this up, you will require a power supply unit. Okay. So, this is the functional block diagram. You can, if you see a digital scratch pad, relay logic. In fact, the relay logic, the architecture for this block, this computer block, is very similar to that of any any computer or with the ALU, etc., that you are very familiar with. Then the setting data, of course, can be stored in the ROM, as we discussed, and then that can be used for computation by the logic system. You then have the analog subsystem, the digital input. The digital inputs could be anything, breaker status, for example, can be a digital input, because it is either open or closed, either 0 or 1, isolator status, open, close. So, there are some digital inputs also which the relay can accept. It is not that it functions only on analog inputs. And then the digital output for the relaying decision. All that you need a power supply to operate. Okay. So, now we will move on to the individual subsystems. The first one, of course, is the analog input subsystem, because your values that you get from the power system, the voltages and currents, these are analog quantities. Now, to convert them into digital quantities, you will need an ADC. We will just look at the ADC very briefly, maybe a couple of slides later. But you can have only one ADC and a multiplexer to sample various values. Okay. So, what you can do is you will need a multiplexer in that case. This is known as a non-simultaneous sampling scheme, and after the multiplexer you have a sample and hold circuit, which is a simple capacitor which will remain charged at that value. So, the sample and hold is required because by the time the ADC computes the digital value, the value itself could have changed. Okay. So, for that not to happen, you will require it to be held at a steady value. So, you use a sample and hold circuit. This is a non-simultaneous sampling system. So, here just to describe it a little in slightly greater detail, this multiplexer is a set of switches. Actually, analog switches means it is just a set of switches which can, the processor will output the address of the switch to be open or closed. Then you can, that particular value will be sampled. Here, unless you are doing some very basic kind of relay, you will require multiple channels or multiple values to be input to the relay. Okay. So, this is the case where you use an analog multiplexer and then you use a single ADC, because this is more true of the earlier generation of numerical relays, where the ADCs also had a significant cost. Now you get it on a, it's quite cheap to say the least. So, you can have multiple ADCs also. So, the accuracy of the analog multiplexer depends on the output impedance or the impedance, rather the impedance at the output terminal, and the sample and hold circuit is just a simple capacitor. So, you get a impedance in the range of 10⁻⁸ to 10⁻12 ohms. So, very high impedance. So, there is no problem in this case. Okay. So, here this is the sample and hold circuit, just a simple capacitor where once the switch is closed, capacitance will hold the voltage at a particular value, and that can be then used for by the ADC. In case you are wondering that we are talking of voltage here, so what happens if we are sampling currents, then you will need a resistance here in the output, so that the current is converted into a voltage signal and that can be sampled. Now, when you are sampling multiple values or multiple quantities in a non-simultaneous sampling scheme. So, first you are sampling, in this case if you see this example, you are sampling VA first and then VB. Okay, but the problem is that they are not the values at the same instant of time. Okay, so you may require that for some processing if you want to compare the two voltages or whatever, I mean, or you could want to compare the two currents. Then what do you do in such a case? You can use some, because these are numerical and you have your program logic to help you, you can use some kind of interpolation using your software that you write, that you have in here, when you sample VA at the next instant, first sample was A, now the sample is B. So, instead of getting D, what you could do is, because you have C and D, you could get the interpolated sample E. So, and for your processing or your relaying decisions, then you use B and E instead of B and D in this case. Okay. So, or you can use some other correction also, you have some relative phasor information and then you use some correction. So, that depends on, that is why you have different relays and different algorithms and different manufacturers using different algorithms. So, this is just one way that is discussed, a simple way, which is interpolation. Okay. Now, you could have multiple sample and hold circuits also in this case, and the multiplexer which will then get the values from different sample and hold circuits and then pass it on to the ADC and then the microcomputer or your processor. Okay. So, here then you do not require this any kind of interpolation, but you require multiple sample and hold circuits. Then there will be you have input transformers, etc., for isolation, so that there is no electrical continuity between the relay and the network as such. Here you can see that there are resistors, which means that these are current signals. Okay. Okay, so here in this case, all sample and hold amplifiers are set to hold the state simultaneously. So, all the switches or all the sample and hold circuits will be addressed at the same time. So, no interpolation is required, all relative phase information is also preserved. So, these generally, I mean, one kind of ADC used is successive approximation ADC, which has a conversion time of about 15 to 30 microseconds. So, you have to account for that. One point which I would like to make here is, here this timing signal or the at which the sample and hold amplifiers are set to hold the state can also be global. So, if you obtain it from a GPS signal, then you can have simultaneously not only in the same relay, but all across all devices or across all relays in the network. That is how PMUs operate, but you could have it with relays also. You get relays which can do that. Okay. So, then after the ADC, you will have an anti-aliasing filter, which is nothing but a low pass filter with a cutoff which is one of the ADC rate. So, the high frequency, because you do not require, we will see why it is necessary to sort of cut out or filter out the high frequency components, because you could get aliasing and the signal could be aliased to another signal, etc. So, now we will see that in probably the next class, but suffice it to say that an anti-aliasing filter is nothing but a low pass filter. Okay. So, we will quickly have a look today at these two devices because they are kind of important, the ADC, successive approximation ADC, and the anti-aliasing filter. A very quick look, not very detailed because we are not discussing those devices as such, but just to have a overview of these, and then we will move on to other aspects of numerical reeling. Okay. So, for an ADC, one of the or the principal feature is the length, word length in bits. Okay. So, suppose which was popular earlier, now you get with higher resolution also, the 12-bit ADCs were 12 bits, 12-bit ADCs rather, sorry, not bits. Okay. So, this implies that the highest positive for a 12-bit ADC, the highest positive number that can be measured is 7FF, and the negative, highest negative number is this. Okay. Okay. So, in other words, the positive number in decimal is 2047 and the negative is minus 2 raised to 11 is 2048. Okay. And generally the analog input will be in the range of plus minus 10 volts. So, each bit what does it represent? One bit 10 by 2048. So, if you calculate this, it is about 4.883 into 10 raised to minus 3, that is millivolts. Okay. So, one more aspect or one more feature of the ADC is that what is the equivalent input change for one digit change in the output. Okay. So, for one digit change means what by how much should the input change, so that you get a 4.833 millivolt change, that because that is your step in the output. In this case, I mean, if we have a 10 plus minus 10 volt and a 12 bit ADC. Okay. So, the output hexadecimal 1 bit. So, 001, this is the output hexadecimal. So, it represents any input voltage between this 4.833 minus half of this and plus half of that. So, 2.442 to 7.352 millivolts. Okay. So, then we come to the next with this we come to the next important aspect, which is known as the quantization error. Of the ADC. So, in general, if we were to generalize this, if if you have an ADC of n bits and maximum input voltage is V volts. We have now from this example, now we are generalizing the quantization error. The Q is equal to V upon 2 into 2n minus 1 volts, or V, I am sorry, 2 volts into V. volts. If you talk in per unit, in terms of per unit, you divide this by V, then the per unit Q is 2 raised to minus n. Okay. So, these, I mean, the word length and the quantization error are the two things that you need to be, I mean, if you were to design relays, these are the two things that you need to be aware of. The next one is the next sort of block in that chain is what is the anti-aliasing filter. Okay. Okay. So, this, as we said, is a low pass filter. The ideal anti-aliasing filter, of course, would be, the characteristic would be, if this were the gain and this were the frequency, this would be the cutoff frequency. But this kind of filter is not realizable in actual practice. So, what you will get is something like this. Okay. So, and this frequency will have to be one of the ADC sampling frequency. So, I mean, these are the aspects of selection of the ADC cutoff frequency, etc. So, that we will see a little more in detail next time. But one way of, the simplest way of doing this is a parallel RC circuit. So, this is, I am not putting any values to this, because if this is in general that I am drawing the circuit, and just okay. So, this is the simplest form of an anti-aliasing filter. Of course, this is a passive anti-aliasing filter. You could use op amps, etc., and make it into an active filter. What you do is you simply, I will just draw without putting any values to it. I will draw the resistance elements, I will leave as it is. This is an op amp in the output, and this this part I have actually removed from here and connected. Okay. So, this is an active filter. So, we are not getting into filter design, etc., because that is not the aim of the course. Before we close, I will just show you a block diagram of the of a type of ADC, which is the successive approximation ADC, and then we will close for today. Because you should be aware of how an ADC operates. I should have mentioned it before we started low pass filters, but somehow slipped. So, we will. This is a variable gain amplifier. These are the analog inputs. Then after that you have a comparator. Then you have an up down counter. Then you have an ADC output resistor. This is the output. Okay. Okay, then after this you have a, what are you comparing it with? So you have a digital to analog converter here, and this values you will compare. Okay, this is a variable gain amplifier. Okay, so you get the analog input, you compare, you set the values, the digital counter up or down, then you compare, you convert it back to the analog value and compare if there is a error. If there is an error, you go back to this loop and keep incrementing or decrementing it till the error is reduced to whatever is the design threshold, and once that is done, then you can get the output. So this is a block diagram of a successive approximation ADC, and as we said, the approximate conversion time is about 15 to 30 microseconds. Okay, so we will have a look at the final slides before we close for today. Okay, the successive approximation ADC and anti-aliasing filter we have just looked at. So in summary, these are, we have discussed this once in the class, in the earlier classes during the very beginning of the course, but here we are just sort of comparing, just to conclude that cost wise probably the numerical relays are the cheapest today. The others are not all that expensive. Maybe electromagnetic relays, because they are so out of production and you require coils and magnets and all that, they will be more expensive. Self-checking is there available with numerical and solid state relays. Integration and flexibility, functional flexibility is not just getting values from other relays and then changing the settings. It could also mean that with the proper inputs, the relay can be made to function as another device also. An overcurrent relay with proper, if you could give voltage inputs from the substation LAN or arrange for VT inputs, you could also have it function as a distance relay. So you have functional flexibility also. This is will be more and more apparent in the coming years when when protocols like IEC 61850, standards rather than like IEC 61850 get implemented. So functional flexibility, adaptability, this will not be available with the other two relays, will be available only with numerical relays. Okay, and finally some thoughts that I will leave you with, so that you can think of answers for this yourself. Can relaying hardware or protection hardware be used for measurement purpose? Either way. Can relaying hardware be used for protection, and for protection hardware being used for relaying? Remember that in relaying the currents can be very high. Okay, while in measurements you need to accurately measure even the smallest of currents. So for example, if we talked of 12-bit ADC, so the resolution at the bottom of the scale could be poor. So in which case you may not be able to measure a current as low as 1 ampere when you have to measure the current as high as say 10,000 amperes. Okay, so that's why the same hardware, this can happen with CTs also, because if you have very low currents for protection CTs, they have to be, we saw that 20 times and all that. So if you have currents which are current transformers which are accurate to 20 times, getting those same current transformers to be accurate for very small currents, 1% or 2% like that, is difficult, because the magnetizing current of the CT itself will be very high. So this kind of compromises will be there. The second is, though we talk of adaptability and interoperability and all that, many of this hardware, software, etc. is, and the software that drives the relaying is proprietary in nature. So though theoretically you could take a relay and then next relay can be from any other manufacturer and then integrate and all that, practically it becomes a little difficult, because all the software, firmware, etc. is proprietary in nature. So but the future is towards open source and open source kind of protocols and relaying. So this is just some food for thought for you. We will close here, and then next time we will look at in a little more detail about at sampling. Okay, thank you.